Okay, we're back. Now we start the scientific session 2, Novel Computing Paradigms. In this session, we will learn about the projects on machine learning and AI with effective applications in projects with innovative methods in different domains. We welcome Felipe Tobar, our chair. Felipe Tobar is a civil engineer in electricity from Universidad de Chile, a Master of Science in Electrical Engineering from the same university, and PhD in Adaptive Signal Processing from Imperial College London in Adaptive Signal Processing. His research lies between statistical machine learning and signal processing. He will be sharing this second scientific session. Thank you, Felipe.
Hello, can you hear me?
Yeah, we can hear you loud and clear.
Thanks very much for hosting this and for organizing the event. I'm very excited to be chairing this session, for which we have an amazing set of talks. So, without any further introduction, I would like to present Romain Rouveau. He is a full professor of computer science at University of Lille, and he's going to present about the Green AI and Sustain project.
So, hello everybody. I'm Romain Rouveau. I belong to the Inria Spirals team, located in Lille, in France, the north of France. And I'm going to talk about towards an ecologically viable machine learning approach that contributes to a more sustainable artificial intelligence. So this work is done in collaboration with many partners, and I'm going to share some of the early results that we obtained, in particular in the context of an associate team with Inria Chile in particular. So as a matter of motivation, 10 years ago, there was an observation that IT sector was actually attracting more and more energy in terms of energy consumption. It was actually competing with some of the biggest countries in the world. So this growth in terms of energy consumption raised a lot of attention from the ecosystem, trying to better understand actually what was the causes of such a huge energy consumption and what could be done, more importantly, to reduce this energy consumption and contribute to have a more viable approach to the way we do IT. Apart from that, there was also energy forecasts that were trending and predicting growth in terms of energy consumption. So asking ourselves this question about what we can do to reduce the energy consumption of IT was definitely a critical question already at that time. So we were 10 years ago, a decade ago. And since that, actually, this kind of question has become kind of a regular question, a recurrent question from both the industry and academia. That's often the case that when we deal with energy consumption, most of the people think that energy consumption is an hardware problem. And the solution will come with new hardware, not software. So this was the claim of Joe Armstrong, who was the father of Erlang. And he was kind of convinced that the biggest gains and savings, in particular when we talk about energy, will come actually from designing better hardware and not from designing better software, which is in practice somehow true, because we can observe that the hardware industry does a lot to reduce the energy consumption of hardware and design more and more complex architectures to try to save energy. And we'll come back to that later in my presentation. But still, we can ask the question about software, because software is actually driving the hardware. I mean, the way you use application on your laptop or on your servers drives the access to resources which themselves consume energy. So asking ourselves what we can do at the software layer is definitely worth interest. This is particularly worth of interest because a decade ago or so, Marc Andreessen actually wrote a news about software that was eating the world, and why software was actually eating the world. So 10 years later, we can observe that definitely it was true. Software is eating the world, it keeps eating the world, and is eating many other domains nowadays. So it's worth investigation in terms of energy. And in particular, we can observe that now even AI is eating software. So artificial intelligence is being deployed in many domains, in many applications, and covers many domains of systems that are deployed in our daily life. One example is in the domain of software engineering, which is the domain I belong to, is a recent release of GitHub Copilot, which is a service that helps developers to write their code. And GitHub Copilot leverage actually the OpenAI Codex model, which is a huge model that has been learned across millions of repositories of code, and actually builds knowledge of all these repositories to now provide a new service to developers that can write code and correct code on their behalf. So when we face this kind of trend and this kind of services that are released every day, so we have the example of GitHub Copilot, but we can imagine that this kind of services are becoming mainstreams in many domains, and there will be probably more of such services that will be available in the upcoming years. We can ask ourselves about AI sustainability and what is the sustainability of AI? What is the cost of artificial intelligence, of machine learning algorithm in particular in the future, and what we can do to improve the situation? So there are both the question of what is the cost of AI, what we can do to measure the energy consumption of such algorithm, and then there is a question about how we can improve the situation and what are the levers that we can use to improve such a situation. So this question has attracted attention from the machine learning community a few years back now, that were considering actually the cost in terms of carbon emission of training new models, in particular the use of deep learning in the case of natural language processing. And actually, the colleagues who did this study observed that the training of the new neural architecture can be really huge compared to usual emission of inhabitants in the US. So this is particularly important to raise as a community, as a researcher, to understand actually that our activities in terms of research and our adoption of machine learning in particular can have some strong incidence on the environment, and that we need to be more concerned about the impact of our research on the environment. So we started to do some experiments on our side and trying to understand what was the effective energy consumption of machine learning. So we started with some simple experiment where we tried to train a gradient boosting classifier. So we took the scikit-learn framework, which is a framework that is developed by Inria, actually, by some team at Inria, and we took some of the examples that are provided with the framework to try to understand actually what was the real cost of machine learning. So we used some of the toolkits that we developed in our team to perform the measurement. And what we did is that first we train a new model, and we can observe that the cost of training a new model can be huge, given the exponential of the measurements that are reported in this graph. But more interestingly, we tried to give some insightful measurements for the practitioners. So we tried to go beyond the raw measurements that can be reported in terms of joules, which is the usual measurement and unit for reporting energy, and try to compare it to the cost of a single inference using the same model. And what we observe is actually to train a gradient boosting classifier, we need actually almost 4.1 million inferences for reaching the same level of energy consumption, which means that as long as you don't use 4.1 million times your models, you are somehow actually paying the cost of training, a huge cost for training this model instead of actually using it. So this is particularly interesting because this raises a question about the frequency at which we should train such kind of model, because if you are not using this model because it is used for just a basic feature of your application, for example, this means that you should probably consider actually training such a kind of model less often than if this model is used on a continuous basis. So that was the first observation we did. And then we move also to the question of the accuracy of the models. So typically, what is the cost of training a model and how the accuracy evolve along training? And what we observe is that if you spend, let's say, 1 unit of energy to train a model, you will reach 0.65 accuracy, which is kind of okay for a model. But if you want to improve this accuracy by 0.1, then you will have to spend twice more energy than you did before. So this is also one common phenomena that is known in learning, actually, is that when you want to get the best accuracy out of your model, you should be ready actually to spend a lot of energy and probably waste a lot of energy to try to maximize the accuracy out of your model and your training set. So we also try to deeper investigate this point, and we move into actually how the energy consumed by this model is spread across the different components of a typical computer that is used for training such a model. So this time we took the Cypher 10 model and we tried to train it, and we consider actually the evolution of the energy consumption compared to accuracy as we did before. But this time we also split the curve across the different components that are involved in the learning process, which means the GPU, the CPU, and the memory. So we still observe actually that whenever you want to increase the accuracy by 0.1, you will spend more and more energy to get this increase and get a better model. So you should be ready actually to waste a lot of energy, which again raises the question of what is the desirable performance and accuracy you want for your model? Do you always need a 0.99 of accuracy for every single model, or you can accept actually a lower accuracy if you are inclined to save some energy? And what we also observe is actually the energy is spread across not only the GPU, because we often talk about the GPU, but also the CPU. And the role of the CPU is also kind of important in the learning process. And we can observe that not only the GPU consumes a lot of energy, but also the CPU will have a huge impact on the energy consumption in the training phase. So to try to improve the situation, we also consider actually what was the effect of the CPU affinity and processor affinity, and try to see by adopting a different configuration of the process, the application that run on the GPU and CPU, we can observe some impact on the energy consumption. So we took the standard configuration of Cypher with default parameters for executing the application. And by actually playing around with core pinning, which is a technique to assign the process to some specific cores of the processor, we observe that we can actually save up to 22% of energy without changing the application, without doing anything about the data set, and reaching the same accuracy. So here the system aspect of machine learning and artificial intelligence shows that actually having a wise configuration of your software and hardware layers can basically help to save energy by improving the performance of the training phase. So that was a very interesting result actually, because you can get such an energy gain quite easily. It doesn't need to train some specific model aside to run the experiment several times. You just need to adopt some best practices for running your application. The other aspect that was interesting to investigate, and we started to investigate, was the adoption of AutoML, which is getting increasingly used by practitioners, because when you use machine learning, you have to tune some hyperparameters. So when you do that, actually, you need some deep expertise, and you need basically a data scientist that knows a lot about the models and the data to select the appropriate parameters to use. While with some frameworks like AutoML and up to now in particular, you can delegate this task to the software, and the software will optimize itself to find the best hyperparameters for your model. But this comes at a cost, an energy cost again. And typically our observation have shown that actually you would spend 25 times more energy actually to find the best model with the best hyperparameters compared to a standard training that will be based on scikit-learn, as I've been showing before. So using auto machine learning approaches can be interesting if you are a practitioner, but again, in terms of environment, it's a huge cost that you will have to pay for that. So all those measurements, we did them with some frameworks that we developed as part of our team. So the framework is called Power API, and this framework is actually an answer to a growing concern of developers and practitioners about how we can accurately measure software energy consumption. So that's a framework that we developed as open source software for several years. And these frameworks actually helps practitioners to better understand the energy consumption of their software. But to do that, actually, they have often to leverage the complexity of hardware architecture. So I mentioned before, hardware architecture are becoming more and more complex because actually the actors in this domain are doing their best to reduce the energy consumption. And to do that, they implement and combine several heuristics within the processors to work at different frequencies. So the processor can adjust the frequency depending on the workload, but they also combine this with sleep states that can be activated by the processor to save energy when it's not at work. So having this more and more complex architectures that keep moving along generations, they keep integrating new features into the processor. It makes it very difficult to follow in terms of models that we can build manually to understand the energy consumption of such hardware. So our solution actually that we embed in Power API use itself a machine learning approach, but we try to use a kind of lightweight machine learning approach to learn the power model of such complex architectures and then use the power models to follow the energy consumption of software. So one of the features that we use in our model is continuous learning. So we keep optimizing a model that we try to learn. So we learn this model from measurements that we collect in real time because our systems are intended to be deployed continuously in data centers, in cloud computing infrastructure. So we keep having new data coming as new performance metrics. And one of the first challenges that we have to solve is to find what are the best features to build this power model. So usually computers expose what we call performance events. So performance events are raw information that are exposed by the processor. And we have to select among the hundreds of performance events, the ones that are the most correlated with the power consumption. And that's what we do with this first layer that try to identify actually what are the most relevant performance events that we can use. And then we use them into a lasso regression to learn the power model of the system. And once we have the power model of the system, we can use this power model to do a software energy consumption estimation. And what is interesting in this approach is that actually we keep challenging our model and check whether this model is relevant and accurate. And whenever we observe that we diverge from the ground truth that we can obtain from an interface like Intel RAPL, we can trigger actually the learning of a new model or improve our current model. And we observe that by doing that, actually, we succeed in building models automatically that are kind of accurate enough to do the energy consumption estimation, because at the scale of a computer, we have less than 2 watts of error on average, which is particularly low compared to the energy consumption of a processor. So that's an overview of the approach that we apply, that I mentioned. So we need to monitor performance events and do that dynamically, because there are a lot of performance events and we cannot monitor all of them at the same time. So we need to sample the performance event, because we have a very limited number of slots to measure performance events. So that's a specific aspect that we need to take into account. Once we have selected these events, we build a model for the host, using a lasso regression, and this regression is then used both for power estimation as a scale of a software, a single software, so we can tell you how much your Zoom client is currently consuming, or how much your Firefox browser is consuming, and we can do that for every single application of your laptop or your server. And at the same time, we use the same model actually to make sure that we do not diverge from our ground truth. And if needed, we trigger some model calibration to be sure that we can keep using our model. So we try to make our model as sustainable as possible to avoid training of new model every single night. So typically, that's the kind of graph that we can show to users. And on the top, you can see the energy consumption of the processor itself. So you can see the ground truth and the models that we learned. So we can observe that the model looks quite accurate, and then we can disaggregate the energy consumption across the different processes that are run by the system, including the kernel. So we run on top of Linux, and we can observe what is the energy consumption of the kernel, but also different kind of applications that we can run sequentially or even in parallel. We can also report energy consumption compared to hardware consumption. So we can relate the energy consumption of software with the energy consumption of hardware. So here you have an example of the energy consumption of several benchmarks that run on a CPU and DRAM components. And we can observe actually how the energy distributes across applications. So that's interesting when you have a parallel applications that use several processors. You can see how the energy distributes across the hardware components. And this can help a practitioner to understand actually how the energy distributes and what are the levers that can be activated to try to reduce this energy consumption if needed. So this is described in some of the papers that we publish on Power API, and these specific power methods that we call SmartWatt, which is an instance of Power API that implements the approach that I just described. And finally, we also developed some additional tools to help developers to better understand the energy consumption of their software. So this is a tool that is called Joule Hunter that actually helps Python developer, because Python is one of the popular framework and programming language that is used by practitioners in the domain of machine learning and AI to develop software. So that's a tool that actually will allow developers to dive into the energy consumption of their software and to help them to understand what are the pieces of code that are consuming energy in order to help them to reduce the energy consumption of the specific pieces of code and not focus on the wrong parts. So to conclude, there are a few challenges that I want to raise on this topic of sustainable AI. The first one was reasoning on sustainable performances and questioning the desirable performance for machine learning models, because accuracy comes at a huge cost. So we need to take this into account and probably think about actually what is the reasonable performance that we can expect from a model, and not try to learn the best and the most accurate model for every single case of application. We also consider more and more carbon emission, because in particular with GPUs, the cost of hardware is not negligible, and we need to also think about the efficiency of hardware and whether we always need to go for the latest version of hardware. And maybe there are a lot of cases where we can accept to run on an older generation of hardware, but with maybe performance that are not as interesting as newer generation, but with a global carbon emission that is more reasonable. And energy mix can also be something to consider depending on the location of the processing. We more and more consider energy-bound learning and try to learn with energy budget. So what we can do with a given energy budget, and how we can spend this energy budget to do a learning with a more intelligent approach, and not just put a raw data set in front of a learning approach and try to see what happens. So this is something that needs to be considered, in particular in the case of competition for machine learning algorithm. We also consider more and more the exploration of the cost of federated learning. And here, federated learning is intended to improve the privacy of learners. And we try to see actually how we can balance privacy and environmental objective and find some equilibrium between these two objectives. We also think that investigating reuse of partially trained model is worth investigation and worth consideration in the case on the environment, because sharing knowledge is maybe more interesting than keeping learning again and again on top of the same data. So the way we manage trained models or partially trained model is important, and in this domain, learning from software engineering is also something that we want to investigate to see actually what we can borrow from software engineering community in terms of best practices for handling models, because in this domain, they have been handling models for quite a long time, and they have some good practices that we could be taken as example to handle machine learning models, and typically versioning on top of Git is one example of practice that could be worth investigation for handling models. So that's it for my presentation. Thank you for listening. And if you have questions, feel free to get in touch, and I will be happy to answer.
Well, thanks very much, Romain, for the presentation. And now we move on to the second presentation by Nicolas Tabarot. He is a senior researcher and head of the Gallinet team at Inria. Nicolas is going to present about Gecko, which is a gradual verification and robust proof engineering for COG. This talk is going to present the outcomes of the associate team called Gecko, which is a joint effort between Gallinet at Inria and the Playat team at Universidad de Chile. Please, Nicolas, go ahead.
Hello, everybody. So I'm here to present the Gecko project, which is about gradual verification and robust proof engineering for COG. So first, a bit of context. So Inria here in Nantes and the Pléiade team at Universidad de Chile has a long-standing collaboration with many associate teams over the last 10 years, and a lot of visits in both directions to Chile and to France also. And we have also many common publications. And quite recently, just before the COVID crisis, we managed to organize the CAS Summer School, which was a 1-week immersive school on the Coq-Proof Assistant, which happened in Querón del Maipo. And so this school was really a success. We had almost 100 applications. We could only accept 40 of them for space issues. And so we managed to make it free for students and principally for students in South America. And so thanks to many fundings we had, we managed to organize this school that I think bring a lot of knowledge to students in South America. And so now I will explain a bit about some of the feedback the scientific feedback that we had on the GECKO project. So the GECKO project was about improving access to program certification, in particular in the Coq-Proof Assistant, which is a proof assistant developed by Inria. And so the idea is to make program certification more amenable to software engineers, in particular by improving how proof engineering or proof refactoring is done in the proof assistant, and also by adding a notion of gradual verification. So first, let me explain a bit what are proof assistants. So there are several interactive proof assistants on which how theoretical work can be applied. So as I said already, the Coq-Proof Assistant on the Inria side, but other competitors are available for instance, the Agda Proof Assistant developed mainly in Sweden, and the Lean Proof Assistant that has been developed recently by Microsoft. And the idea around all these proof assistants is to get a programming language in which the notion of specification that you can give on your function is very rich, and so rich that you can also specify exactly what is the behavior of your program. So for example, if you consider the head function that you could define on list, you can give it a more precise type by saying that the head function only apply to a list of size at least 1. So for example, using the traditional vector types that you can define in Proof Assistant, you can specify the head function to only accept as input list of size at least 1. But you can also express more evolved specification that you can call lemmas in that case. Then you can say, for example, that if you apply the head function to a list that contains A at the top, then you return the value A as a value. And so all these proof assistants are based on a very strong correspondence between formulas and so formulas on the logic, on the programming, on the logic side, and types on the programming side. And even more importantly, there is a correspondence between the program that you can write and the proof that you can do on your logic. And so what you need to remember about this is that this kind of interactive proof assistants are really based on the fact that you're manipulating at the same time a programming language and a logical system, and proofs and programs are already two sides of the same coin. And so, as I said, in the GECKO project, we want to make program certification more amenable to software engineer, because the fact that there is this strong entanglement between proofs and program is very rich from certification point of view, but it's also very complex, and so it can make the system harder to use for software engineers. So we want to leverage a bit this difficulty here. So one first achievement of the project has been the definition of univalent parametricity. And so what univalent parametricity provides is a strong connection between isomorphic structure. So for example, if you're trying to develop a program based on natural number, for efficiency issue, if you want your program to run fast, you may want to use binary natural number as you mainly most of the time do with your mainstream programming language. But the difficulty is that if this notion of natural number is very fast with respect to execution, it's quite complex to reason on binary natural number. For example, if you just look at the addition of the specification of addition is already quite complex, and proving simple things such as commutativity of addition may become very hard when you're manipulating binary natural number. And so on the other side, there is a notion of unary natural number, just defined by 0 and successor. And this notion of natural number is much easier to reason about. So addition is very simply defined, and proving properties about addition and multiplication is quite straightforward. But on the other side, it's very slow with respect to execution, because you don't have this exponential acceleration of binary natural number. And so what we have defined during the Gecko project is a way to automatically lift properties on programs proven on the easy to reason about specification, to lift it automatically to equivalent properties on the efficient representation. So being able to execute the efficient one when efficiency comes in the picture, and to reason on the easy to reason one, so on the other one, when you want to do a formal specification of your program. And so this automatic lifting has been enabled by the mix of two very important notions in proof assistant, and in particular in type theory that there is behind the scene. And so these two important notions are parametricity, which somehow is some kind of uniformity principle on the functional side of your program. And the other very important notion is univalence, that has been developed almost 10 years ago now in the homotopy type theory univalent foundation. And so this principle gives some kind of representation independence, so gives you access to the fact that if two structures are isomorphic, then this means that you should be able to go from one structure to the other without too much pain. And so by mixing these two principles, the uniformity and representation independence, we have been able to provide an extension of the Coq proof assistant, in which it is actually possible to switch between the efficient and the easy to reason about representation. So now I would like to focus on another achievement of the Gecko project. So as I mentioned previously, we wanted to provide a more gradual point of view on program certification. So what do I mean by gradual? So this is in the setting of gradual typing, which is a kind of theoretical notion that allows to mix static and dynamic typing. So for example, there is a gradual extension of Python. So Python is a dynamically typed language, and you can add some more static guarantees on it, but gradually without being forced to going fully to a statically typed language, such as, for example, the Coq proof assistant. And to do this, there is a special notion of question mark dynamic type, the unknown type, which is some kind of wildcard that you can give to any type, and in particular to untyped part of your program. And somehow the key idea of gradual typing is to be optimistic. When you see the unknown time, you always assume that it could have the type that you expect, and this optimistic typing phase is counterbalanced by the fact that at runtime you check that actually the piece of code that you were given an unknown type actually behave as expected, and if it doesn't, you can fail with a nice error message. And so the idea is that this notion of gradual typing can be used to allow for more incremental certification inside interactive proof assistance. So let me explain a bit what we mean here by looking at a typical scenario that you can have. So going again on list of some size, the vector of size n. So if you want to develop a program certification based on the vector library, you may want to program the filter function that takes a vector of size n and filter it by removing all the element that doesn't satisfy the predicate p here. That for any a returns a boolean whether the value satisfies the predicate or not. And so if you want to define such a filter function, you quickly have an issue just by giving the right specification, the type of this function, because actually the size of the return list depends on how many elements have been filtered out and how many elements remains in the list. So it's quite complex to specify the type, because you need to provide the size of the list that you don't really know upfront. So one possible situation in the presence of gradual certification would be to just say that actually we don't really know the return size of the list. We just know that it exists and that there is a size, but we don't want to specify it. And in a gradual setting, it will be possible to apply this filter function to a given list, and then apply the head function out of it to get the first element of the list that satisfies the predicate. So for example, in this particular situation, the predicate is being even. And so if we filter the list 1, 2, 4 by the fact of being even, what we get is 2, 4. And so we can perfectly get apply the head function out of it, and we get 2, because 2 is the first element of 2, 4. And to the opposite, if we filter the empty list, the vector nil, then we get as an output the empty list again. And so if we apply the head function out of it, then we will get a runtime error by saying that there is no head to the empty list. So this is the first step. So you see here that you have postponed the static verification that would have make sure that the return list was of size at least 1 by the unknown type and the unknown natural number in that case, that lets the system being optimistic about the fact that there will be at least one element, and failing at runtime when it's not the case. And so what do we mean by gradually certifying your program? Is that now you can try to be a bit more precise about your type to avoid runtime failure, and to defer to static typing, the fact that you will reject this program. And so you can try to give a more precise type to filter. So now you say that the return vector is not of any size, but it's on a size that is computed by a function cons that counts how many elements in the list satisfies the predicate p. And so this is actually the correct way of fully certifying the filter function, fully specifying the filter function. And so if you then you can gradually say, okay, I don't want to define con for the moment. So if you still put a question mark to the definition of the function con, then the system behaves the same. But you can also gradually start to specifying the con function by saying, okay, now I know that if you give me the empty list, then there is nothing to filter out anymore. So the return size of the list must be 0. And if you give me a list constituted by a head and a tail, then I will defer to later the specification of the function. But already by just defining this, starting to specifying a bit this con function, you can see that in the case of the filter applied to the nil function, you're now able to statically reject this function, because the system will be able to compute that filter applied to the empty list will return a list of size 0, and the head function cannot be applied to a list of size 0. So you will be able to statically forbid this application in that case, and still being able to compute the correct value in the case of the previous list 1 to 4. Okay, so this is the ideal setting that what we wanted to implement. And one of our first result was a kind of a negative result, because we have been able to show that actually it was not possible to have in the same setting. So the nice property that we want on programming languages, which are called progress and preservation, saying that actually if your program is well typed, then it means that it will evaluate and preserve the type during evaluation. Another property that is very important for proof assistant is normalization of function, because this is the property that guarantees that your system is consistent and cannot prove the false proposition. So this is a very strong property that is required for a programming language to be considered as a logical system, being able to show that there is no proof of false. Another important property is to be conservative with respect to the theory already implemented inside proof assistance, and in particular CIC in the case of Coq. So this just means that we provide gradual certification as an extension of what is already going on, and not as a new complex or ill-behaved system. And the last property is adding this notion of graduality, and by this I mean the notion of precision, saying that the unknown type is the less precise type somehow, and if you give a less precise type to a program, it still evaluates correctly. If it could have a precise specification, then the unprecise evaluation behave correctly. And so we have been able to show that actually it was not possible to get all those properties together, because by just using graduality and conservativity of a CIC, it's always possible to define a non-terminating function and to break normalization. And so one of the main outcome of our work was first to realize that the ideal situation was not possible, but we have been able to solve the tension by actually taming a bit this fire triangle and weakening this notion of graduality. So we realized that the traditional notion of graduality, which was done on simply type setting, was not completely adequate in the rich setting of proof assistant. And so by weakening a bit the notion of graduality, we have been able to avoid this fire triangle, and still being able to have a system which is conservative over what was already implemented inside proof assistant, still satisfies normalization and so consistency, and get strong guarantees that correspond to a weakening version of graduality. So we're still able to show that if you have a less precise certification of your program, it will behave the same as a more precise one. What we just remove as a basic property is the fact that the unknown type or the unknown term is always less precise than the more precise one, because it depends on some very complex situation that you can only encounter in the proof assistant setting. Okay, so based on this, we have been able to propose a gradual extension of Coq that now needs to be implemented a bit more for real, because it's just done on a prototype version, but it requires more work to make it really usable inside the proof assistant. Okay, so I just want to conclude on the picture of the CAS Summer School, and thank again Inria Chile for his participation in this very successful school that happened now 2 years ago, and we hope to be able to organize such a nice event in the future when the pandemics will be over and we'll be able to organize this kind of thing. Thank you, and I'm ready to answer any of your questions.
Well, thanks, Nicola, for the presentation. Our next presentation is by Abdelkader Lahmadi. He's an associate professor at the University of Lorraine. And Abdelkader is going to present Angel, an IoT e-health platform to monitor and improve quality of life. In this presentation, we will see a mechanism for adaptive monitoring of low-power IoT devices using reinforcement learning.
So hello everyone, I am Abdelkader Lamadi. I am associate professor at University of Lorraine and a member of the RESIST research group at Inria Nancy Grand Est. My talk is about reinforcement learning for adaptive monitoring of low power IoT networks. I did this work with a PhD student, Mohamed Said, where we are interested in developing a new technique based on reinforcement learning to monitor low power and loose networks, Internet of Things. So the outline of my presentation is the following. First, I will give an introduction of the problem that we addressed in this work, the proposed approach, some results with simulation and experimentation, and finally, I will conclude and provide some future work regarding this research. Firstly, low power IoT networks are mainly composed of few thousand to thousands of nodes, which are limited, device and constrained with limited power, memory, and processing resources. Regarding this type of networks, they are low power at their link layers, and also they are unreliable with high loss rates and low data rates. For example, some networks provide between 20 to 250 kilobits per second. So in these networks, we have different monitoring challenge and requirements. First of all, the challenges of the monitoring of these networks are basically to provide accurate information about the network in a timely manner with link and signal quality, like link and signal quality, connectivity, density, the battery level of the nodes, or the packet loss rate or delays. However, these networks are carrying both sensing traffic and monitoring data. So we have to handle this because monitoring and sensing data will contend, and we need to preserve the channel time for the primary task, which is the sensing. Regarding the requirements, we need a monitoring solution that is lightweight with reduced resource consumption, robust to fault and fault tolerant, to avoid the wireless channels effect, and it needs to be distributed, not relying on the specific node. So in the previous work, we developed this approach, which will be based on reinforcement learning. So we formulate this monitoring problem as a reinforcement learning with reinforcement learning method, where we embed in each monitoring node a reinforcement learning agent that is able to decide about the polling intervals to meet low power network constraints and monitoring requirements. So this agent will act on the environment to adapt these polling intervals, and we will get rewards from the monitoring process to be able to decide on these polling intervals. I will give more details later. So firstly, let me describe the architecture of our monitoring system, which will be based on a polar poly architecture. So in this network, we will deploy polar nodes and poly nodes. So the polar nodes are the main agents that will collect attribute values, monitoring attribute values from the polys, which are the nodes that will provide the monitoring data. So each poller will send the requests to its poly to collect attributes, and the poly will send the responses to the poller. So this is the monitoring architecture that we are relying on. And we deploy this learning agent on each poller to collect attributes values, adapt polling frequencies to minimize the monitoring packets, and detect all anomalies on this collected data. So the approach that we are developing, as I said before, is relying on reinforcement learning technique, which is an experience-driven technique of machine learning, where a learner, which is this agent, autonomous agent, will make an experience by a trial and error process in order to improve its choices in the future. So we need to define three types of variables to build this reinforcement learning agent. The first variable that we have to define is the state space of the agent, the action space, and the reward function. So I will detail each of these variables that we defined for this reinforcement learning model for monitoring. The first is the state space, which is defined as a couple of the current polling interval in seconds selected by the agent and the quality of the monitored variable during the last interval for each node and each time. So the polling interval will take discrete integer values in the range t-min and t-max, where t-min is the minimum sampling interval used by the IoT application, and respectively the t-max will be the maximum interval used by the application. Then we defined the action space of the agent. So we defined three types of action. The first action will increase the polling interval. The second action will keep the current interval. And the third one will decrease the polling interval. The third set of parameters is related to the reward function, which is the reward that will get the agent when it takes an action on the polling interval, for example, to increase, decrease, or keep. So we define this reward as following. It's a combination of the current selected interval by the agent divided by the minimum sampling time and multiplied by a beta, which is the numerical representation of the monitored attribute quality during this polling interval. So this value beta will take 1 if no anomaly is detected, and it will take minus p, where p is the number of threshold crossings. So the idea behind this reward is if an anomaly is detected, we will penalize the agent to increase its polling interval to detect more threshold crossing and detect more anomalies. So this is a reward. This immediate reward represents the trade-off between a cost and the quality of the polling interval. So the next step, we evaluated the performance of our approach. We used two methods. The first one is based on simulation by using OpenAI simulator, GIM, c'est the GIM simulator. And the second one is based on experimentation with the Contiki-Kuja simulator. So our simulation setup using OpenAI GIM is the following. We used this simulator and we defined three types of monitoring variables that represent the CPU utilization. These variables have three different behavior. The first one is uniform change. The second one is a normal change. And the third one is a self-similar change. The quality is defined as good when the monitored CPU utilization is under a fixed threshold of 60% that we get from a previous work published by Mujumbi in 2018 in the NetSoft conference. And the attributes are generated for a duration of 8,000 seconds. So this is our simulation setup using OpenAI simulator, Gym Simulator. And we define these performance metrics, which are the accuracy that represents the ability of the reinforcement agent to correctly decide to raise or not an alert in each time step. The second one is the detected anomalies, which is the ability of the agent to correctly raise an alert for all occurred anomalies. And the third one, which is about the cost of this monitoring, which is the number of transmitted monitoring attributes packets per node. So firstly, we evaluated the effect of some learning parameters on this performance metrics. We were interested in two types of learning parameters, which are the learning rate alpha and the discount factor gamma. We observed that the accuracy in our approach is greater than 95%. Why? Because the percentage of false positive is equal to 0 in our situation. Since the agent can miss some threshold crossings, but it is not able to detect false threshold crossings. So for this reason, we have a good accuracy. For the attributes which are the uniform change and the self-similar, the best results are obtained with lowest learning rates and higher discount factor values. However, for the normal change attribute, the percentage of the accuracy increases slightly with the learning rate and reach the best rates when the values of gamma are low. So this is what we studied regarding these parameters used by the reinforcement learning agents are the alpha and gamma, and we identified these parameters, the optimal values of these parameters. Then we studied the convergence analysis, which is the ability of our agent to detect the anomalies. We compared three temporal difference functions used by reinforcement learning, which are the k-learning, the SARSA technique, and the expected SARSA. We compared our approach with the notification-based monitoring, mainly where e-pollers are programmed to send monitoring packets to the poller at a fixed interval. We used the 4 configuration. In the first configuration, we have 1 packet per second. The second one, 2 packets per second, 4 packets per second, and 8 packets, and a packet every 8 seconds. So this is a static configuration based on notification. So then we analyzed this configuration and we compared their performance with our reinforcement learning approach. What we found that our approach provides better performance than this static configuration, as we see in this table. For example, for the uniform change, we have 86% of detected anomalies compared to 12% for a packet each 8 seconds, or 55% for a packet each 4 seconds, or 48% for a packet each 2 seconds. As we observed also that when we change the reinforcement learning technique, we obtain different performance. For example, the best percentage for the normal change is obtained by Q-learning. However, for the uniform change and self-similar, the best performance is obtained when using expected SARSA. So our RL-based polling approach shows better performance compared to static notification-based monitoring approaches. Then we did some experimental tests using the ContiQOS and the Kuja simulator that emulates a Zoltaria Z1 modes. we use the following settings. We fixed the alpha to 0.9 and the gamma to 0.1, and we choose the Q-learning temporal difference method. So we obtained mainly results regarding the number of exchanged monitoring packets. So what we observed that the conclusion that we obtained that the number of packets sent per the reinforcement learning based monitoring nodes is lower than static 1 and static 2 by approximately 73% and 55% respectively. We found also that reinforcement learning agent detect almost 11% more anomalies than the static 2 configuration, with only 8% more packets in the network. So as we see in this figure, we observe that our monitoring based approach, our monitoring approach based on reinforcement learning provides good performance compared to the static configuration. We observe also that the static configuration with one packet per second has a high number of monitoring packets. If we decrease the number of packets per second, for example, one packet is 8 seconds, we have low number of monitoring packets, but we will have also low anomaly detected. So for this reason, our approach gives a good trade-off between the cost and the quality of the detection. So to conclude this talk, in this work, we provided a monitoring approach based on reinforcement learning to monitor some parameters or attributes of low power IoT networks. We observed that the performance varies mainly according to the monitoring attribute behavior. We checked 3 types of behaviors, which are this uniform change, normal change, and self-similar changes. We compared our approach with the static reporting intervals, and we observed that our approach shows a better percentage of detected anomalies with decreasing bandwidth consumption and which will conserve the node's energy. So as next steps for this work, we are working on extending our approach with multi-agent reinforcement learning technique to achieve a global optimization. So instead of using one agent, which is separated from the others, we will build a technique that based on multiple agents that communicate with each other to globally optimize this monitoring of a low power IoT network. So thank you for your attention, and don't hesitate to make a question. Thank you.
Well, thanks, Abdelkader, for the presentation, and we are now going to move to the Q&A session, where we will have the speakers available to answer your questions. So I would like to remind the attendees that we have a section in the Livestorm system where you can input your questions, and we can look at them here, and of course the speakers are going to try to answer them. I would like to mention that Nicola is not available now for sharing this with us. So in his representation, I believe Eric Tanter is going to be here. So we have 3 questions so far. I would like to start with the first one, which is for the first presentation by Roman. I don't know, Roman, if you can read the question. Shall I read it out loud for you?
I read it, but you can read it maybe for everyone.
Okay, yeah, good. So Jaime is asking whether there is an application or maybe an application under development that measures the energy consumption used by a specific part of code, for example, in C or C++.
So yeah, so this is something we have been doing in the past, actually. So I can share the link of a previous PhD thesis that's been delivered where we did that a few years ago. So far, it has not been ported to the newest version of the tool, but that's something we can consider in the future if there are people interested in doing a measurement of their C or C++ code. Because for some cases of application in HPC, for example, this is something that could be worth investigation.
Great, great. So I am not sure whether Eric or...
Yes, I'm here.
Yes, you are. Okay.
Sorry, had to reboot. Hi, Roma.
No problem. Yeah, that happens. And I'm not sure whether Abdelkader is around or not, but we can continue. There's a couple of there's one question, I guess, for your presentation by Andres Viñaga. He asks, he says, Coq allows high order types, and he asks if you deal with types of types in your approach.
So yes, basically the answer is that's one of the main interesting of the challenge. Basically, that's what makes it much harder and much more interesting than just gradual typing for normal type systems. Basically, so yes, obviously. Right. Look, you can ask for more details later, but I doubt.
Well, Andres, if you're listening to this, please feel free to put more details. And I remind all the attendees that you can enter questions here in this field. Now there's a question. The third question is for Abdelkader. Luis is asking how much additional energy is required by the reinforcement learning method compared to other static ones.
Yeah, thanks for the question. We, to be honest, we haven't assessed evaluate the energy cost in a rigorous way. But what we did that we reduced the communication part. So when we reduce this communication, we will also reduce the cost, because the most costly part in IoT is this communication, because to send, to receive, and even if they are battery powered, so this will have a large impact. So we haven't a real measurement of the cost of the energy on the device, but by reducing this communication part compared to static notification, we are able to reduce the communication cost of the monitoring of this kind of devices.
Thanks very much for the answer. We have a fourth question by Pablo, which is for Romain. Pablo asks, how widespread is the concern about sustainability in the AI community? If he's asking if there are special groups or research networks dedicated to this issue.
So it's actually a growing concern for the AI community, in particular in machine learning, because so far it was they were aiming to improve performances of models, and they were somehow actually trying to get the best computers to try to learn as much as possible and get the most accurate model by actually leveraging the hardware that they were using. But recently, they did observe that actually the carbon emission related to machine learning activities, in particular training for supervised model, was kind of getting huge. And that started to be a motivation for doing something about sustainability. So that's something I mentioned in my presentation. And there are some papers on arXiv trying to do some estimates of the cost of learning for natural language processing. And more and more people are getting concerned about that. There are also trends like Google working on TPU and Google reports that the energy consumption of TPU is way less than traditional GPUs. But still, we don't have access to TPUs to do this kind of measurements in lab. And yes, and some things that start to raise and mention in my perspective is that they would like to do more learning based on budget, energy budget. So you are given an energy budget, and we are going to compare different algorithms by consuming this budget. So you can actually adjust your pipeline of activities and try different strategies actually to see what are the effects in terms of both performances and energy consumption.
Very good, very good. Thanks. There's a compliment for Andres' question. He's saying, thank you, Eric, and he's asking how do you deal with the topmost type of all types? So the type issue.
The type issue. Well, so we just do exactly what Coq does, right? So there's a bit of context. This goes back to Russell and so on, that with the set of all sets, that if you do a logic where you don't have any kind of stratification and you can quantify over the same things you're defining, you can basically define paradoxes, and so have an inconsistent logic. So all the consistent proof assistant have an escape to that, which is the same as Russell from last century, which is to just stratify. And so basically there's not one type, but there's one notion of type living at a level of what's called a universe level. And so type doesn't have type, but type at level I has type at level j for any j greater than I, strictly greater than I, and this way you avoid the loop. And so when we do the gradualization, we do the same. And actually, so if you're interested in those universe issues and consistency and so on, then our work is even more interesting, because the key to address the tension that Nicolas talks about in his talk is actually to change a bit the way we deal with universe levels, to be a bit stricter in some cases in order to avoid non-termination in the presence of gradual types. So yeah, I guess that's it. Thanks, Andres, for your questions.
Thanks, Eric. Well, in case you have any questions, please let me know, and if you want to complement anything in your presentation, this is the time, of course. I have one question for the Green AI for Romain, the presentation. So the first one is that you mentioned that when you are trying to go to the very, very detailed part of the training stage, like you are investing a lot of time, effort, and energy, as we saw in your presentation, for getting that little extra accuracy. I was wondering if that has been connected with the sense of the statistical significance of that optimum, because of course when you're training with data, your data is finite and a partial representation of the world. So at one point, becoming or asking a finer and finer value for that parameter is statistically insignificant. So you're already in the error bar, if you want to put it in that way. Mm-hmm. So I was thinking that maybe there's a way to connect the criteria for not using too much energy because it doesn't make sense, but also statistically it doesn't make sense.
Yeah, I totally agree, and that's somehow the kind of question we raised in our measurements, the quality of data, and to which way actually the data contribute to increase the quality of the model. At some point, for sure, you are reaching some kind of optimum, and any data that you will add to the training phase won't contribute that much to the quality of the model. So that's a point where you need to identify actually whether you need to feed the model with more data, whether you have samples that are worth to be trained, to be included in the training phase, or whether actually the samples are just the same as before, and in terms of statistical significance, does not bring any much value. So that's something that is very interesting in terms of being able to decide actually when you need to stop training. The thing is that so far, with most of the tools that are provided and toolkits, that's often the case that people actually feed the algorithm with a data set that they have, and they hope to get the best out of this data set. So they don't try actually to stop the learning as early as possible by considering that actually the data does not bring any much value actually into the training.
Right. Thanks very much. Makes complete sense to me. I think we're all done with this Q&A. There are no more questions. I would like to give a last chance for the attendees to put anything else in that box. Maybe that's it. So I'm also very happy with the session. I enjoyed the talks. Thanks for being available for the Q&A, and thanks for the videos as well. So with that, we close the session. I would like to thank the speakers for being here. And I give the microphone to Daniel. Daniel, please.
Thank you, Felipe. I enjoyed the talks too. Thanks again, Felipe, for leading, for being the chair of this scientific session. Also, thanks to Romain, also to Abdelkader, and to Nicolas. Also, thank you for everything. Have a good day.
Thank you. Thank you all.
Goodbye.
Well, this is how we successfully conclude our first day at the Journées Scientifiques Inria Chile 2022. We remind you that in order to participate in the following days, you must be registered in each part. If you forgot to register of any day, you can go to journesscientifique2022.inria.cl and you will find there the registration links in the program section. You will also be able to find interviews with our keynotes and more. We remind you to follow us on Twitter and LinkedIn, Inria Chile. Finally, we remind you that tomorrow the Gather Town session will also be available, so we can continue networking and exchanging ideas with our interns. So this way, we close this session for today and meet again tomorrow at 8:30 a.m. in Santiago de Chile and 2:30 p.m. in Paris. Thank you to all the participants, and see you tomorrow on the second day of Journées Scientifiques Inria Chile 2022.